Welcome to the video Spheroidal Graphite Cast Iron as a material for casting, part 1. Why cast iron is a material for casting? The reason is that liquid iron is added with carbon, and as in all solutions, increasing the solute concentration into the solution, the freezing temperature is decreasing. So this make this material iron with carbon easy to be melted at a much lower temperature compared with the pure iron. And this makes advantages in processing and advantages in solidification behavior. And spheroidal graphite cast irons are typically eutectic alloys, nearly in the surrounding of the eutectic. That means that it's the lowest possible melting point of an iron alloy. But we have a problem. When the liquid iron with the carbon is freezing, the iron and carbon tends to combine together, producing carbides. Carbides makes the iron brittle, and they make machining very difficult, and they are good material for abrasion resistant, but not for machinery constructions. So typically iron and carbon are also added with silicon. Silicon is an element that increases the activity of carbon. In this way, during the freezing process, carbon is able to escape from the iron combination, so avoiding the formation of carbides and promoting the formation of free graphite. This is also connected to the cooling rate during freezing. It means it's connected with the casting thickness. And this is also helped with the inoculation. That means the addition of some silicon and other elements, parts, into the liquid melt before freezing, and this making external heterogeneous nucleation that accelerate the process of freezing, of solidification in a separate form between the iron matrix and the free graphite. So, but we have different shapes where this graphite can form. The most common is the natural shape is a lamellar graphite shape. What does it mean? It means that because of other elements that we have in solution, example sulfur, the surface tension of the liquid iron is low, and this low surface tension make easy to present a large surface for a unit volume, as it happens with the lamellar graphite. So after at the end of the Second World War, it has been discovered the spheroidal graphite iron that is essentially made by subtracting sulfur from the liquid melt using magnesium, and in this way, subtracting sulfur from the liquid metal, the surface tension is doubling. And with the high surface tension, the natural shape is the one that minimizes the external surface of graphite per unit volume, and this is a spheroidal graphite. So this addition of magnesium and the combination of magnesium and sulfur can be done in different way, that depending on the process facilities and the process optimization for each foundry. So we have the Tundish covered system, we have the wire system, the HEMOD system. So in this all the years that passed, 75 years that passed from the end of the Second World War, we had different evolution of processes. So another difference that we have between the lamellar graphite iron and spheroidal graphite iron is given by the solidification pattern through the freezing. You know that when you, from the liquid, you transform the liquid into solid, you have a release of a latent heat. And the rate at which this latent heat is released is very important in determining the solidification pattern. For lamellar graphite iron, we have a normal diffusion in the liquid from the liquid, from the carbon of the carbon contained into the liquid to the lamellae, graphite lamellae that are growing by addition of new parts, new atoms of carbon during solidification. And this happens into the liquid, so it is very fast. And fast separation of carbon from the liquid to the austenite and to the lamellar graphite takes a short time with a high heat rate of latent heat release. This latent heat release is transferred to the remaining liquid that it's freezing in a so-called stratified way. So we have a progressive solidification from the metal that is in contact with the mold, and it's a progressive solidification up to the central part of the thickness. It means that each time the lamellar are growing because of carbon deposit, we have expansion of graphite into the melt that helps the self-feeding. So feeding a lamellar graphite iron is typically easy, and it is easy to get sound casting. For spheroidal graphite, the process is different. Around a graphite spheroid, we have a deposit of a solid austenite. And so the carbon diffusion of the liquid metal to the spheroid, it's given by a carbon diffusion through the solid austenite shell. And this is a slow process with a slow latent release rate. This slow latent release rate in the spheroidal graphite iron makes the metal to be solidified in a large part in a massive way. Most of the thickness solidify at the same time. This is called a massive solidification with an expansion of graphite that is in a short time making a high pressure increase inside the freezing metal that makes pressure on the mold walls that can be enlarged. And this is a source of porosity that we can find into the casting, and we need to avoid by a proper risering. So for ductile iron, it is much, or spheroidal graphite cast iron, is much more important than with the lamellar gray iron, the risering, and also the filling the mold to avoid slags to enter into the casting that can come from the magnesium and sulfur reaction. So the mold engineering, the mold layout must be more professional for ductile iron castings that happens with lamellar graphite iron. For this reason of slag entrapment and for avoiding porosity, but also associated to the higher mechanical properties that spheroidal graphite iron has in respect of lamellar graphite. And this is done typically using numerical simulation of filling the mold by using Navier-Stokes equations, and also simulating the heat transfer into the mold using the Fourier equation, but coupled with a material modeling that is able to simulate the latent heat release following the mechanism I described previously.